Hello everyone, my name is Rosangela Caicedo and today I will present my project for IE 5300 titled Generative AI for Airfoil Design Generation and Aerodynamic Performance Agreement. In this project, I will explore how generative AI and machine learning can be combined to generate aerodynamic design candidates and evaluate their performance automatically. The goal of the project was to demonstrate how AI can assist engineers during early design stages by exploring many possible configurations faster than traditional approaches. The objective of this project was to design and evaluate a generative AI prototype capable of generating airfoil design candidates and predicting the performance. The system predicts aerodynamic noise using a machine learning method, and it estimates aerodynamic efficiency using simplified equations for lift coefficient, drag coefficient, and lift-to-drag ratio. Overall, the goal was to demonstrate how AI can support engineers decision making by automatically exploring multiple design possibilities. So our problem statement, aerodynamics and aerocaustics performance depends on operator and flow conditions. Even small changes in variables such as angle of attack, velocity, or boundary layer thickness can significantly affect aerodynamic behavior. Traditional evaluating these changes requires many simulations or experiments, which can be time-consuming and computational expensive. Because of this, I decided to investigate whether AI could help automatically to the exploration of potential design configuration and identifying promised candidates more efficiently. This project follows the builder or technical track. In this track, the objective is to create a functional AI prototype rather than only performing theoretical analysis. The prototype integrates aerodynamic calculations, machine learning models, and generated sampling techniques. Together, these components simulate a simplified AI assistant workflow where the system can both predict performance and generate new candidates configurations. For the system architecture of the prototype, first, the system receives input parameters related to aerodynamic conditions. Next, the data is processing and using to train several machine learning models, including KNN, random forest, and support vector regression. After training, the model are evaluated and compared, and the best performance is selected. Finally, the model is integrated into a generative design model, which creates new configurations, calculates aerodynamic metrics, and runs the results for visualization. So after training the machine learning model, I implemented a generative design process. The system generates multiple candidates, operate configurations based on the range and the input data. For each separated candidate, the training model predicts SSPL, which represents the aerodynamic noises. The simplified aerodynamic equations are used to estimate lift coefficient, drag coefficient, and lift-to-drag ratio. Finally, the candidates are ranked according to aerodynamic efficiency, allowing the system to identify most promising configurations. After generating many results configurations, the system evaluates them based on the aerodynamic efficiency. The candidates were ranked using the lift-to-drag ratio, which is a common metric for aerodynamic performance. The best configuration achieved a lift ratio of approximately 15.67, representing the highest efficiency among the generated designs. The results demonstrate that this AI prototype can explore the design space and identify promising aerodynamic configurations automatically. So this slide shows the link to the functional prototype that I will show in a couple of minutes, which was implemented using a Google Colab and a radio interface. The prototype includes data preprocessing, model training, and evaluation, as well as the generative design model. Users can interact the system by entering a text prompt, and the AI will generate candidate configurations, predict their performance, and return the ranking results. This interactive interface demonstrate how AI tools can be used in a practical engineer workflow. Now we'll proceed to show the prototype. To build the system, I used several approaches to guide the development process. First approach was using to load the dynamic dataset and identify usable variables. The result was to define the real dataset structure and select the features. The other approach was to help build the random forest regression model to predict SSPL. The result was creating the predictive model for the prototype. Additional approaches were using to generate candidates configuration and calculate aerodynamic metrics such as lift, draft, and lift-to-draft ratio. And finally, prompts were used to create the integrated gradual applications, which serves as the final prototype. The results for those three were added the generative design model, added engineering-based screening metrics, and created the final functional prototype that is much stronger for my presentation. For the system evaluation, the generated candidates remained with the realistic parameter ranges, which indicate that the generated process produced reasonable outputs. The moral accuracy was strong, since the predicted SPL values closely match the actual values of the dataset. The hallucination risk is relatively low because the system used numerical formulas and trained models rather than unrestricted test generation. Additionally, visualizations of the feature importance and residual plots help interpret the model behavior. Even when AI system performs well, human validation is still essential. In this project, the generated candidates were checked against simplified aerodynamic theory. The list and drag ratio followed expected trends, and the configuration with the highest lift-to-draft ratio corresponded to the most efficient design. This confirms that the results are consistent with the analytical equations used in the prototype. However, in real engineering applications, engineers will still validate the designs using CFD simulations or physical testing. Ethical considerations. The use of AI in engineering also raises important ethical considerations. Simplified models may generate unrealistic outputs if they are applied outside the dataset range, so validation is necessary. Human oversight is important to ensure that AI-generated results are interpreted correctly before being used in design decisions. Transparency is also critical, so engineers understand how the model makes predictions and what limitations it hits. Finally, large AI systems can require significant computational resources, so efficiency and responsible use of computational resources should be also considered. For more information, you can visit the link below. Based on the results of this project, several improvements could make the system more powerful. First, using a large and more diverse dataset will improve the model generation ability. Second, integrating high-fidelity aerodynamic simulations such as CFD could validate the generated system. Future work can also explore advanced generative models like bidirectional autocoders or GAN. Finally, incorporating additional aerodynamic variables such as the Reynolds number and wing geometry will allow the system to generate more realistic configurations. In conclusion, this project developed a generative AI prototype for airfoil design exploration. Several machine learning models were competing to predict aerodynamic noise, performance, and random forest provided the best predicted accuracy. The system then generated multiple candidate configurations and evaluating them using simplified aerodynamic equations. The best configuration achieved a lift-to-drag ratio of about 15.67, demonstrating the potential for AI or design exploration. Overall, this work shows that generative AI can support engineers by helping them explore efficiency design solutions more quickly and systematically. Uh, that's all my presentation. If you have any questions, you can ask. Thank you so much.